Okay, in this lecture, what we're going to do is go over an example out of the book, the first example in chapter 10. So we are going to review example 10.1. So what 10.1 says is that we want to find what is the charge and the current for a electric potential which is 0 and a vector potential, A, that is mu 0 some constant k divided by 4 times the speed of light times c times t minus the absolute value of x, that thing squared, pointing in the z direction. Let me make that z look a little prettier. Okay, so it looks like that when the absolute value of x is less than ct, and a is going to be equal to 0 when the absolute value of x is greater than c. So if we're at some distance, which is further away from speed of light times the time, then there is no potential. It's only in this range of basically minus ct to positive ct that we get this potential A. Okay, and so if you think about it, what we've done is we've measured the vector potential and the scalar potential. We've measured V and we've measured A, and we want to know now what is creating these potentials. They must be being created by some kind of electric charge or some kind of current. So how can we do that? So if you're just before we get started, I just wanted to emphasize that K is a constant and that C, the speed of light, we can solve for as 1 over the square root of epsilon naught mu naught. Okay, that may come in handy a little bit later. Okay, so what we're going to do is we're going to start with our definitions of electric and magnetic field in terms of potentials. So the electric field we found in the previous lecture was minus the gradient of the potential minus the time derivative of A with A. Sorry, time derivative of A. Okay, so now we can plug that in. And what we find is that over the space, that essentially that x, the absolute value of x greater than ct, electric field is 0 at x less than ct. Now my electric field is the gradient of V is just 0. V is 0. Minus the time derivative of this function right here. Okay, so that would be the time derivative of mu 0 k over 4c ct minus x quantity squared in the z direction. Okay, so that if we can work out that derivative, so that derivative is going to be minus 2 mu 0 k over 4c, and then the derivative on the inside would be c. I'm sorry, ct minus the absolute value of x. Okay, so we took the derivative of that once. We now apply the chain rule, and we get an extra c right there. All of that in the z direction. So therefore, an electric field in this range is going to be minus mu naught k over 2 ct minus absolute value of x in the z direction. Okay, now what about B? B is the curl of A, and so in that range of x less than ct, then what we have to do is take the curl, and what we get is when we work out the curl is we get minus mu 0 k over for C, the x derivative of ct minus the absolute value of x squared in the y direction. And so since it's an absolute value of x, I essentially get plus or minus mu 0k over 2 c ct minus the absolute value of x in the y direction. And the plus and minus is you get plus, whoops, you get plus when x is greater than 0 and minus when x is less than 0. Okay. And just to reiterate that for x greater than ct, then the electric field and the magnetic field are both going to be 0. So it's only in that range. Okay, so now we've worked out what the electric and magnetic fields are going to be. So let's apply them to Gauss's law, Maxwell's first equation, and then from there we can get the electric charge. So the divergence of E is going to be essentially what you get is it's only in the z direction. The electric field's only in z, so that divergence is going to be the z derivative of our equation minus mu 0k over 2 ct minus the absolute value of x. And if you notice, there's no z dependence in any of this, and that's going to be 0. So right away, we've now found that our electric charge is 0. No electric charge in the problem. Okay, so let's take a look at the magnetic field. If we take the divergence of the magnetic field, then what we would get is the only vector direction to the magnetic field is the y direction. So when I take the divergence, I would get a derivative with respect to y of plus or minus mu 0k over 2c ct minus the absolute value of x. And in the end, there is no y dependence, so that is also 0, which makes sense because the divergence of B should be 0, and no matter what the case is. If I now look at the curls, the curl of E would be zero, 0. Basically, there's only a z dependence to E, which in the end would give me which in the end would give me essentially the time derivative of B. So if I take the time derivative of B, I get minus plus mu 0k over 2 in the y direction. So the curl of B, I can work out the same thing. B only has a y dependence to it. What I can work out of this is essentially the time derivative now of E. So the time derivative of E is going to give me minus mu 0k over 2c in the z direction. And so if I look at this, what I have is the time derivative of the electric field is minus mu 0 kc 2 in the z direction, and the time derivative of B is plus or minus mu 0 k over 2 in the y direction. And what I find is that I've already determined that the electric charge is 0, but what I also have from all of this is that the electric current is also 0. So I've got, so going through Maxwell's equations and plugging in these potentials, what I find is that we have no electric charge and we have no current density at all. So that seems kind of perplexing. Now we've got these, we know we've got electric and magnetic fields because we have potentials, but we don't have a charge density or a current density. So what we can look at now is, let's look at the boundary. So let's look at what's going on. So at x equals 0, for the magnetic field, there is a discontinuity. And so what we find is that there is a surface current in the xy plane. I'm sorry, the xz, the yz plane. So we have a current So in here, we have this current flowing in that plane. And when we apply that boundary condition, what we find is that 1 over mu 0, the parallel component of field 1, based on one side of the plane, minus the current, the current, the field, the parallel component of the field on the other side of the boundary is equal to our surface current crossed into the direction of that area, which is essentially x. Like there. Okay, so let's plug in now this to our equations. So we have 1 over mu 0, mu naught k over 2c, ct minus 0, x is equal to 0, minus 1 over mu 0 minus mu 0 k over 2c, ct minus 0, and all of that is equal to k free crossed into the x direction. Okay, so now if we were to try and work this out, what we would get is 2, the mu zeros cancel, the c's cancel, and what we would have is 2 kt over 2 in the y direction is equal to kf crossed into the x direction, or kty is equal to the current density over the area crossed into the x direction. So if the vector crossed into x produces a vector that's in the y direction, then kf must be in the z direction. So what we find is that kf is the constant k times the time in the z direction. So it's interesting. So what we find in this problem is that there is these electric and magnetic potentials in this space. On either side of the YZ plane, there are no basically volume currents or volume charges. But in the plane at the origin, inside this YZ plane, there is a electric current, a surface current flowing in the plane, which is now producing V and A throughout all space.